So dear students, in this video I am going to solve one more numerical in module 3, which is nothing but vapor power cycles, right? So the numerical goes like this. A steam enters the turbine of a steam power plant operating on Rankine cycle at 10 bar 300 degrees Celsius, full stop. The condenser pressure is 0.1 bar. Steam leaving the turbine is 90% dry. Calculate the adiabatic efficiency of the turbine and also the cycle efficiency, neglecting pump work. So this is the problem. So this is the problem that we are going to solve today. So what is the data given here? Steam enters the turbine of a steam power plant operating on Rankine cycle 10 bar. So that means P1 bar is taken as 10 bar. So here two pressures are there. So in this he has taken as P1 and P3, or anything you can take as P2 and P3. So on top of it you can take at the second point you can take P2 bar, and third point you can take P3 bar or P1 P2. So it depends on your comfort. So you can take two different pressures, that is one pressure is 10 bar, the highest pressure is 10 bar, and T is equal to 300 degrees Celsius. The condenser pressure is 0.1 bar. This is one more pressure. This is the smallest one. So 0.1 bar. Steam leaving the turbine is 90% dry. So this line is very, very important, because this line shows that steam leaving the turbine is 90% dry. That means if it is 100% dry, it is exactly this will fall on the dry saturated line. You can see in the diagram, see 2 to 3 process is there. So 2 to 3 dotted line is shown in dotted line. That is 100% dry. That means it is coming and falling on the dry saturated line. Now in this problem it is given as 90% dry. That means it will not come and fall on the dry saturated line, but it will go inside the dry saturated line. That is why you can see 2 to 3s. That is a straight line. It is not a dotted line. So 2 to 3 is a straight line and complete line, not dotted line. So 2 to 3s, that will give you the turbine, the steam leaving the turbine is 90% dry. That means some amount of wet or moisture is present in the steam. So after spinning the turbine, when steam leaves the turbine, then it is some amount of moisture content is present in there. So that is the meaning of this, is very important. So we should not take this dotted line into our consideration 2 to 3. Instead we need to take 2 to 3s. That is what we need to take into our consideration for solving this problem. Next, calculate the adiabatic efficiency of the turbine and also the cycle efficiency, neglecting pump work. So in this problem we need not worry about this pump work, which is nothing but H4 minus H1. So that is what the pump work is. H1 to H4, that line will give you the pump work. So since the pump work remains so small, so he is asking us to neglect this pump work. So this is how we have to solve the problem. So P1 is equal to 10 bar, T2 is equal to 300 degrees Celsius, and they have taken it as P3, the smallest one, 0.1 bar, and X3, that is 90% dry. That means X3 is equal to 0. That is dryness fraction X3 indicates, and we need to find out the turbine efficiency and cycle efficiency, and we have to neglect the pump work. So we need to take the steam table book, and for P2, here in this line they have taken it as P2. Earlier in the diagram it is shown as P1, but here it is taken as P2. So don't get confused. You can take any notation, so need not worry about that. But here there is a small correction to be made. In the diagram they have shown as P1, and in the calculation they have taken it as P2. So P2 is equal to 10 bar and T2 is equal to 300 degrees Celsius. So in that, if you from steam table book, if you check, so H2 is equal to 3052.1 kilojoules per kg. This is Hg. So if you see the steam table book, you will find 3 different enthalpies like HF, HFG, Hg. So in that you need to select the Hg value, because that will show you the dryness dry enthalpy, dry saturated enthalpy, right? So at 10 bar you need to take H2 is equal to, that is Hg is equal to 3052.1 kilojoules per kg. In the same line, the same pressure, if you check the entropy value, that is Sg. So since it is the second point, he has taken as S2. Otherwise, you need to check Sg value for 10 bar pressure. So it will come as 7.1251 kilojoules per kg. So this is the entropy value and this is the enthalpy value for the pressure 10 bar. So another one, so for table A1 that is given, so that is not mandatory. The same what you call dry saturated steam you can take from steam table book. So P3 is equal to 0.1 bar. If you take, you will get TS is equal to saturation temperature 45.83 degrees Celsius. So in that HF, HFG, SF, SFG. If you see on top of it, you did not, so we have not taken this HF, HFG since it is in the superheated. You can see in the diagram, TS diagram, this P1 is shown here marked as, marked in the superheated region. So we don't need that HF and HFG value. But 3S is inside the dry saturated. It is in the wet region. It is not in the superheated region. That is why this time they are taking it as taking SF, SFG, HF, HFG also. So you should not get confused why they have taken the extra values, because these values will be used for calculation. So HF, HFG, SF, SFG. Why they have taken these many values? Because it is in the wet region, right? So in this slide, what you can see is from steam table book, you have to refer to get all these values. You have to turn the P2 10 bar pressure. So you have to take all the values and you have to check the 0.1 bar pressure. So you have to take the HF, HFG, SF, SFG. Next, so X3 is equal to 0.9. That's what it is in the data. It is given as a 90% dryness fraction. So that means H3 is equal to HF4 plus X3 into HFG3. This is the formula for enthalpy of wet steam. So H3 is equal to HF4 plus X3 into HF3. So 191.8. So what you have to take is, so 191.8 value you will get here in the steam table. If you see the second value, P3 is equal to 0.1 bar, HF is equal to 191.8. So that value plus 0.9 into HFG3. So you will get H3 as 2345.4 kilojoules per kg. So that is the H3 value. Next, if you take the 2 to 3 process or isentropic process, S2 is equal to S3S. That is what we have seen in this diagram. S2 is equal to S3 is equal to S3S, right? S2 is equal to S3 because entropies are same, equal entropy, that isentropic process. Entropy remains constant. That is why S2 is equal to S3S. S2 already we know from steam table book 7.1251 is equal to SFG4 plus X3 into SFG3. If you solve this, you will get X3 values at the dryness fraction at that point, 0.863. With this, we can find out H3S. H3S value, so 191.8 plus this dryness fraction into 2392.9. So you will get 2257.45. So in this, you have found out the H3 also, H3 value at the same time H3S. Both values we have found out. So next, we are going to find out the turbine efficiency. What is the turbine efficiency? H2 minus H3 by H2 minus H3S. So you can see in the figure diagram, H2 minus H3, this is one value, numerator, divided by H2 minus H3S. So that will give you the turbine efficiency. So the values already we have found out everything. So you can substitute in the equation and you will get the turbine efficiency as 0.89. That means 89% is the turbine efficiency. Next one is cycle efficiency. Overall efficiency we can call it as cycle efficiency is equal to WT divided by QH. WT means turbine work. Where do we get this turbine work? So process 2 to 3s. That means H2 minus H3. Divided by heat supplied. Where do we come across this? between H1 and H2. That means H2 minus H1 will be that heat supplied. So with this, so you will find, but H1 is equal to 191.8 kilojoules per kg. Where do we get this value, H1 value? From steam table book. So if you substitute all these values, you will get 25% as the overall efficiency. Overall cycle efficiency will be the 25%. So this is the simple problem under this Rankine cycle. So numerical on this Rankine cycle is a very simple one. So we can solve this type of problems more in number. That will be useful for your internal examination. Thank you.